Welcome back to machine learning. Today we'll be covering practicalities of machine learning. There are many decisions you have to make as a programmer for a machine learning system. We've talked about hyperparameters before, and those are definitely things you'll spend many hours deciding. But there's a couple of other things that we're going to talk about today. The first is representing data. The second is irrelevant and redundant features, and then feature pruning and normalization. And finally, evaluating model performance. Representing data is the most important choice you will make. We've been talking a lot about categorical data, like this. So we've been representing them as one-hot vectors, which is fine, but it doesn't capture the true relationship between these points. Let's think of another example, like an image of a cat. If we have an image like this, we can represent our data in so many different ways. We can use the raw pixels. Each pixel in an image is just a value from 0 to 255. So if you needed your data in vector format, you could take every column or every row of the image and concatenate them together to get one really long vector. This is not ideal for many reasons. A 10 by 10 image would result in a 100-dimensional vector. But a 10 by 10 image is basically unheard of. It's so small. Even a 100 by 100 image is very small. But that image would result in a 10,000 dimensional vector, which is pretty big. In addition to these feature vectors being really big, they also lose most spatial information. Flattening an image like this removes all spatial cues, which is very important in an image. We could overcome this challenge by, instead of using pixel value vectors, we could keep patches intact, concatenating vectors of patches, but you still lose global spatial information. You can also use shape. You can use contour information and format it as a vector. The options are basically endless. And even more so when we start talking about representing text. If we have a sentence like, "It is a puppy and it's extremely cute," how might we represent that? The typical approach is like the pixel-wise representation for images, throwing away all context information. This is called bag of words. We treat the text like a bag of words, counting each word and representing the text as a vector of counts. This vector is huge, much like the pixel representations for images, because each vector must be the same size as the vocabulary, with many zero entries. We talk a lot about representation now, but when we talk about neural networks and deep learning, you'll see why they've become so popular. They basically make the representation step a lot easier, allowing us to input raw data directly. Moving on to irrelevant and redundant features. Irrelevant features are those that are completely uncorrelated with the prediction task. That is, it has nothing to do with the label. Redundant features are pairs of features or multiple features that are highly correlated, regardless of whether they are correlated with the task or not. Let's think of some examples to demonstrate these ideas. If we're trying to use machine learning to predict if you will get cancer, we have a feature for your hair color and maybe a couple of other things like blood type, weight, height, age, eye color, smoking habits, drinking habits, family history, etc. Eye color here makes no sense at all. This is an irrelevant feature. All these other features likely have something to do with the task, but eye color does not. Another example where we see redundant features. If we're trying to do a height prediction system, that is, we're trying to predict how tall someone will be based on their physical information at age 5, you may collect data such as eye color, hair color, nutrition, height at 5 years old, body mass at 5 years old, and so on. You may have chosen such a small sample size that you found that light eyes and blonde hair are always found together. These would be considered redundant features. Having both of them provides no additional information over having just one of them. And in this case, it is likely that the eye color and hair color have nothing to do with the maximum height of a person. Which of these is the biggest threat to learning? Redundant features are mostly removed, because it provides no additional information. It's annoying more than anything else. Irrelevant features cause some serious problems. What if we're in a situation where an irrelevant feature actually correlates with the learning task? Let's look at an example of a coin flip. We're going to flip 2 coins simultaneously. One will be the label and one will be the irrelevant feature. We know that if we flip 2 coins, they're unrelated. We may end up getting the exact same thing, however. We hope that the chances of this go down as we collect samples. If we flip the coin n times, the probability that the feature is equal to the label is 0.5 to the n. The probability that the feature is not equal to the label is 0.5 to the n. That is, the probability that the feature is exactly correlated with the label, either directly or inversely, is 0.5 to the n plus 0.5 to the n, which reduces to 0.5 to the n minus 1. This probability becomes very small as we increase n. So this is good, right? Not really, since we care about any feature being correlated with the label by chance, not just this one feature. The chance that either of 2 irrelevant features correlate with the label is this, 2 times 0.5 to the n minus 1, which ends up being 0.5 to the n minus 2. If we end up having k irrelevant features, then the probability that any one of them perfectly correlates the label is 0.5 to the n minus k. But this actually gets worse. Irrelevant features can be bad even if they're only partially correlated with the label. How do irrelevant features and redundant features affect the models and algorithms we've learned so far? Decision trees handle irrelevant features and redundant features quite well. Irrelevant features are basically just ignored because decision trees choose the most important feature first. So as long as the decision tree is reasonably shallow, irrelevant features should be ignored. And using our greedy information gain algorithm causes decision trees to ignore redundant features as they provide no additional information gain. K-nearest neighbors treats irrelevant features with just as much importance as other features because K-nearest neighbors is distance-based. Similarly, with redundant features, it has no way of dealing with either of these in an efficient manner. The perceptron uses a weight for each of the features, and so if a feature is irrelevant, the weight will head towards 0. And if it's redundant, where it depends on the data, typically, but sometimes you'll have similar weights, or it will push one weight to 0 and give the other one more importance. On to feature pruning. Feature pruning is getting rid of features that are not very informative or don't occur very often. In text categorization, the word yikes probably doesn't occur very often. So should we get rid of it? Well, this is a slippery slope and you have to decide when to stop removing things. Usually, we choose some small value k and we remove all features that happen in all but k or in fewer than k samples. So the idea is if it happens all the time, we're not that interested in it. And if it happens very infrequently, we're also not that interested in it. Normalization is very important for machine learning. There's 2 main types of normalization. There's feature normalization and example normalization. Example normalization means that each example is adjusted individually. For example, we can adjust each sample so its length is equal to 1. This makes it so that all the examples lie within the unit hypersphere. This allows for easy comparison across datasets with different scales. Feature normalization adjusts every feature in the same way across all examples. Centering and scaling are typical ways of performing feature normalization. In centering, the entire dataset is moved so it is centered around the origin. Scaling rescales each feature using either variance or max value. In variance scaling, each feature has a variance of 1 across the training data. In absolute scaling, each feature has a max absolute value of 1 across training data. These are the different formulas to calculate the different feature normalization methods. We calculate the mean of a particular feature, we calculate the variance of a particular feature, as well as the max. And then we can perform centering using the mean, variance using the variance, and absolute using the maximum. On to evaluating model performance. This is very important. So far, we've been talking about evaluating models using accuracy, but is accuracy really the way to measure success? Let's think about an example. If I took a sample of students in CS 302 and was trying to predict whether or not those students were CSE majors, I would kind of be stacking the deck, right? Out of 100 students, there may be 2 non-CSE students in CS 302. So if I built a classifier and got 98% accuracy, I would probably think I was doing pretty well. But all my classifier is really doing is saying CSE for every person, and it's getting those 2 people who were not CSE wrong. This won't work very well when I try to use it on all the students at UNR. So we need to reframe our problem. We need to think about what our data looks like when we think about evaluating our model. There are 2 major types of binary classification problems, X versus Y and X versus not X. There's a subtle distinction here. Think of X versus Y as dogs versus cats. So your inputs will either be dogs or cats, and your classifier has to distinguish between them. In X versus not X, we're thinking dogs versus not dogs. So the input can be dogs or literally anything else. And the classifier is basically trying to distinguish dogs from everything else. When we frame our problems as X versus not X, we can use some nicer success metrics. We can use precision and recall. Precision is basically, of all the X's you found, how many of them were actually X's? And recall is, of all the X's that were out there, how many did you find? Precision and recall are defined in terms of true positives, false positives, true negatives, and false negatives. A true positive is an X that is predicted as an X. A false positive is a not X that's predicted as an X. True negatives are not X's that are predicted as not X, and false negatives are X's that were predicted as not X. We define precision as the true positives over the true positives plus the false positives. So that's, again, all the correctly classified X's over all of the X's that you said there were, which may not be the whole story. And the recall is all the X's that you predicted correctly over all the X's that you predicted correctly, plus all the things that you didn't predict as X's that were actually X's. I like to think about precision and recall in terms of English because I think it's really important. I don't like memorizing equations. And so I actually think about these 2 things in terms of their sort of English interpretation. So precision, think about the word precise, right? When you're being precise, you're not making any mistakes. Okay, so you're concerned about making mistakes with precision, right? When you think about recall, you're trying to recall all of the information. So it's okay if you make some mistakes as long as you remember all the things that did happen. Okay, so precision and recall together give us a good sense of how the system is working. Now we have 2 metrics, precision and recall, where we used to have 1, accuracy. Many times people will look at what is called a precision recall curve. I have 2 curves here, an ROC curve, which is receiver operator characteristic curve, and then a precision recall curve. They're basically the same thing, they just look different. In an ROC curve, we compare false positive rates with true positive rates. And we see that we're looking for something where we're getting all the true positives and no false positives. So we're looking for something at the top left corner. Whereas in a precision recall curve, we're looking at precision versus recall. And what we really want is to recall everything and also be very precise. So we want something up here in the top right corner. When you have a binary prediction task, the classifier will usually output a real value between 0 to 1 or -1 to 1. We can sort these predictions, and for every unique value, we can use that as a cutoff point for the prediction. So everything below that is predicted negative, and everything above that is predicted positive. So we're basically just changing the normal threshold. And each time we do that, we can record our precision and recall and then plot them. That's exactly how we get these plots. That's why they're so messy looking. So basically, if we have predictions from 0 to 1 and our first prediction is 0.01, then we would say everything at or below that is 0 and everything above is 1. This will give us a situation where we have very high recall but very low precision. As you increase your threshold, the precision tends to go up, but the recall goes down. If you choose the highest threshold you can, you will have a precision of 1, but a very low recall, since you only predicted one sample likely as X. You'll typically plot recall on the x-axis and precision on the y-axis. And the closer you can get to the top right corner, the better. The top right corner shows precision equals 1 and recall equals 1, which is an ideal situation. Sometimes, however, you just want a single number that you can tell you how good your classifier is. This is the F measure. We can combine precision and recall into this measure, and this balances precision and recall together. This is our F1, which is 2 times precision times recall over precision plus recall. This measure favors systems with roughly equal precision and recall. If you feel that recall is more important than precision, you can weight the F measure for that. We have the general formula of F beta equals 1 plus beta squared times P times R over beta squared times P plus R. Let's check out an example. If we let P equal 1 and R equals 0.75 and we calculate the F1, we'll get 0.85. If we calculate F2, we'll get 0.78 because the recall is not as high as the precision. But if we swap these two numbers, we'll still get the same value for F1, but for F2 we'll get 0.93. So in this situation with an F2, we care more about recall than we do about precision. On to cross-validation. Another popular method for evaluating a model, especially when there's limited data, is to split it up. We have talked about splitting the data up into a training set, validation set, and a test set. Cross-validation takes this one step further and actually separates the data in such a way that we can train on different subsets of the data and provide much more thorough testing. There are two main types of cross-validation: K-fold and leave one out. K-fold cross-validation separates the data into K-folds. K is typically 5 or 10. If K equals 5, then 4 out of the 5 folds are used for training and the remainder is used for test or validation. So you'll end up with 5 different models all trained from different subsets of the same data. This allows you to identify good hyperparameters that generalize well. This is pretty typical in research and industry, as you can show how your model varies depending on the input data. With leave one out cross-validation, we simply remove one sample at a time. We train on the remaining data. This is usually done for very small sets of data to see how sensitive the model is to removing one sample. Leave one out is the same as K-fold when K equals N, and N is the number of samples. Cross-validation is typically done on the training and validation portions of the data, with the test set completely untouched. You can either choose the best of your cross-validation models, or you can use the best set of hyperparameters and retrain the model on all the training and validation data and send that as your final model. As a review, we covered representing data, and we discussed how it's the most important choice you'll make. We discussed irrelevant and redundant features and how all of our models are affected by these. We talked about feature pruning and how it's a slippery slope, normalization and how it's a standard process for machine learning, and we talked about evaluating model performance using precision, recall, and the F measure, as well as a new technique, cross-validation. The next topic will cover ensembles and boosting.